Thanks. Yeah, my talk is going to be about neural relational inference for graph neural networks. And we've heard a lot about graph neural networks in a past today, like yesterday, in Reese's talk and also in Peter's talk. And one of the main assumptions that are usually made in these works is that you already know what kind of graph structure you're given ahead of time, and then you run your graph neural net to say model physical dynamics. And one of the questions we try to ask in this kind of work is, what if we're given some kind of dynamics from some kind of mystery physical system, and we do not know like what particles are interacting with each other in what kind of way. So we want to essentially discover the underlying interaction graph and jointly learn to model the dynamical system. And this is work done in with collaborators, both with my advisor Max Welling and also with people from University of Toronto. And the motivation here is, let's say we're given this mystery physical system here on the left, where you have particles moving around in a box. And the goal is now to build a model that can learn the underlying physical dynamics of the system without seeing in what kind of way they're actually interacting. And the way this mystery physical system here is constructed is that certain objects are connected by invisible springs. And by these connections, you have a certain interaction structure. And given this interaction structure, we could just use a graph neural network and you would be able to model this dynamical system very easily. But the question is, can we jointly learn to discover these interaction structures and model the dynamics of the system? And as a main tool for this work, what we use the graph neural networks, and I'm representing here a special case of graph neural networks that are mostly known as interaction networks or message passing networks, where the main idea is you have one function that operates on edges in the graph, where you take a pair of nodes and you calculate. For example, you gather this pair of nodes together, you concatenate them, and you pass them through an edge update function, which here is called FE. And then after you calculate all these edge update functions, which would in a physical system, for example, correspond to forces, you update your node representation by aggregating all these forces, for example, edge updates, and passing them through another node neural network. And these neural network modules, they can be any kind of MLP or any kind of neural network architecture that you can apply on these node and edge embeddings. And the main idea behind this work is that we run a graph neural network first on the original observed system, where we do not know anything about the interaction structure. So we first run the graph neural network on a fully connected graph, where we are like a first initial guess on what the connections might be. And given that, the graph neural network is tasked to predict the underlying interaction structure. So this could be, in this case, could be certain parameters on the edges, whether two particles are interacting in a particular way, or what kind of constant, for example, for a particular force has to be placed on this particular edge. But it could also be other latent parameters of the physical system. And then the decoder part of the model, it is constrained on whatever the encoder predicted for the interaction structure. So the decoder part of the model would now run a graph neural network on this constrained graph that the encoder predicted, and it is tasked to predict or reconstruct the dynamics of the physical system. So in this case, the decode is exactly what we've seen before in previous works. You would essentially just run a graph neural network on a particular interaction structure, and then you try to reconstruct the dynamics of your system. And the encoder now is tasked to basically identify, just from observed dynamics, what kind of underlying structure is in the data. And we can also exchange part of the model with, say, prior physical knowledge. So we can, for example, simply replace a generative model, in this case, with a physics simulator. So we can, because the structure of the model of this graph neural network is the same as many classical physics simulators, where you have pairwise interactions and node update functions. And so we can just implement a physics simulator in say, any kind of language like PyTorch or TensorFlow, and backpropagate through the whole system and optimize these latent parameters here as well. And so we tried this on a couple of simple physical toy systems with increasing complexity in the forces. So in the simplest case, we looked at linear forces where we have bolts connected by springs, and we just have simple spring forces between them by Hooke's law. Then we have charged particles where you have an inverse square law force, and then a Kuramoto model where you have phase-coupled oscillators that are coupled by the difference in the phase followed by a sine function. And the interesting thing is that you can apply the same kind of model also on more realistic data, say motion capture data or sports tracking data, where interactions could be something like a player passes a ball to another player, a player blocks another player. And when we run this model on these dynamic systems, and here we generate data by essentially choosing random interaction structures and running the physics simulator to generate data. And then after generating this observed data, we run this autoencoder model on this data, and we inspect the discovered latent graphs. And what we find is that both if you use a physics simulator as a decoder, or also directly from scratch a learned decoder, which we train jointly with the encoder, that the model essentially finds these latent interaction structures to a high degree without any kind of supervision that we place on the model. And it gets very close, especially for the simple system where you have only linear interaction structure like with the spring system. It gets very close to the supervised baseline where we would actually run the encoder and you provide labels on what kind of interaction structure is given in the model. Now, in terms of moving forward, I think it would be very interesting to connect this also to problems in causality, where you could think about these latent interactions. If you only have binary interactions, a certain particle is interacting with another particle or is not interacting, then you could, and you have directionality in these edges, then you could think of this, you can interpret this latent structure that you discover as some kind of causal influence from one particular trajectory to another particular trajectory, for example. And also scaling this to larger systems and finding different applications in physics, I think, also an interesting direction. And if you're interested in reading more, then I only could cover only a few things of the paper. We also wrote a blog post about this, and the code is on GitHub if you want to explore this. Thank you. Sorry?
Questions later?
Oh, sure, yeah.
Okay, so right next there's a Roy Lederman. So he's an assistant professor at Yale, and he's going to talk about
Cryoelectron. Cryoelectron.
Cryoelectron. Perfect. Oh, and he's bringing some interesting figures.
So because I only have 10 minutes, I'll have to apologize that I'm not starting with a joke. But I'll just jump right into it. So I'm going to talk about cryoelectron microscopy, and so there's physics in it, there's atoms and stuff, but I'll get later to what I think are the deeper connections and what are the questions that I think are maybe of even more interest to the wider audience. So first of all, why am I talking about cryoelectron microscopy? Cryoelectron microscopy is a technology for figuring out the structure of molecules from measurements in cryoelectron microscope. I'll explain in a minute. And what the interesting properties of this technology compared to some other technologies is that it can be used to map the structure of molecules without crystallizing them, which is what you would usually need to do in the classic X-ray crystallography. And it takes measurements of essentially individual molecules, which could potentially mean that if you have a mixture of different type of molecules, you would be able to extract different type of, basically the different conformations. And this technology has been around for decades, but what happened in the last decade or so is that the advancement in technology, detector technology mostly, allow us to get from what was like this kind of blurry resolution maybe even 5 years ago to almost atomic resolution where it really allows you to place each atom, basically. So how does it work? So you take your solution with the molecules, you freeze this in this very thin layer of ice, and you start bombarding these with electrons. Now, Painting this in a molecule is difficult, so I use a cat. So there's a bunch, so I'm going to go back to molecules later, but this is placeholder for a molecule for me. So you get a lot of these, and they're frozen in kind of random orientation. You don't know for each of them how it's frozen. Start bombarding them with electrons, and you get these very noisy images, two-dimensional projections of this potential function, essentially. And it's very nice because we have at least an approximate physical model for this. So we have this forward model, and we get hundreds of thousands of images like these, which are very noisy. We don't know the viewing direction for each of these, and we have to put together this huge puzzle. Because we have the forward model, you could say, well, we'll throw a few assumptions in, and we can write this nice mathematical formulation for this. We can write a huge Bayesian model for this and just optimize it. So actually optimizing this thing to find out what the object was isn't trivial, but actually people got pretty good at this. So now if you have a homogeneous sample that doesn't have a lot of versions of many different molecules, people can actually do a pretty good job at finding and getting very high resolution reconstructions of these molecules. The problem that I'm more interested in here is the problem of heterogeneity. So sometimes you have mixtures of different types of molecules. So these are very similar, but they have regions that are slightly different. And my favorite is, of course, again, this is a placeholder, this cat. So sometimes you have molecules that are flexible. So you have a continuum of different type of conformations mixed together in your, and you want to extract these. And this variability in the structure is really important for understanding what these molecules do, because that's part of their, it's sort of, we're thinking about is sort of these molecular machines, the inner working of these machines. That's like what we're trying to figure out when we're studying them. So this is a placeholder. This is, so I have a bunch of cats like this, and they're on a molecule. Maybe it's difficult to say like what's going on, but on cats, I can tell you the cat is looking in this direction, the cat is looking in this direction, and we all know what we're talking about. So this is what we use for when we start a simulation with this. And I'll get back to molecules. So the first question about this is, for me, about heterogeneity is what is the question? So if I gave you a solution, what would it look like? And then, okay, if I know what the solution should look like, how do we get to it? How do we solve it? So to understand just the basic idea of how, at least how I think about this, if we usually think about this object, it's some kind of a potential. So we think about it as a three-dimensional function, some kind of a sum of basis functions. So that's a way of describing a three-dimensional object. And if you have several of these very distinct objects, then you write several functions like these, and you try to fit every image to whichever one of these it belongs. And that's sort of what's done mostly now. And when you have a lot of different versions or a continuum of different versions, you would sort of have a lot of different models. There is something weird, though, about looking at these different models this way, right? If I put them this way, it might be more visually pleasing to you. But it actually captures some information. So what happened is that I aligned them, and I sorted them by this heterogeneity parameter, so by the state, so which direction the cat is looking at. This does capture some additional information because there is some sense of smoothness or some sense of regularity as you go between these states. So it's not just a combination of arbitrary states. So there's a sense of regularity here, and one way of capturing it is with higher dimensional basis functions. So basically what happened is that we moved from functions from a bunch of three-dimensional functions to, in this case, a four-dimensional function, and we can express it kind of a similar way that we express three-dimensional functions as linear combination of these higher dimensional functions. So this is an early experiment that we did with a cat. So you take these, I think it was 20,000 images of these, of the 25,000 noisy images of the cat. You don't know which orientation it is. You don't know which direction it's taken from. And this is a four-dimensional object that I'm looking at a movie of it. And we generalize this to, so this is an actual molecule. So what we can see here is, so these actually move independently here. I'm moving them together, but we have this, this structure that, this is the static structure, and we can pick up some of the heterogeneity here. We can see these two regions here, these two are moving. Now, let's stop. Okay, so that's what I can cover about this in 10 minutes. So I'll just want to mention some of the questions that come out of it. First of all, I didn't tell you much about the algorithm. What we're using here is Monte Carlo with these Langevin version, which means that we're using these differentiable components, differentiable descriptions of a molecule, of a higher dimensional molecule. So you can say what we're building is a deep network in that sense, because everything about optimization now is or Bayesian view of this is a little bit like deep learning. And we're actually, in the next version, we're going to use PyTorch, so it's the same infrastructure in a sense. I do also have physics here, but I think some of these issues are part of some of the things that are interesting to discuss about this. So you could say, could you use whatever and a suffix net for this, convnet or anything? And for most of these, the answer would be yes, but there's a sense in which we're trying to organize the images. I don't really care about which orientation each image was taken from, but it looks like we need to build something that's invariant to a permutation of 100,000 images and provides us with some kind of model. So it looks like there might be a sense in which we're trying to figure out the viewing directions. There's a bunch of symmetries, rotations, shifts, repromization, permutations of the input that I think came up in many of the talks. We can look at it as a very over-parameterized solution partly because of these symmetries, or we can build more models that come from the physics of the problem. A lot of this is about interpretability, right? Because what we're trying to do is actually get a model that describes the physical phenomena that's underlying all these images. And there's a bunch of classic problem noise, and do we want to go into deeper modeling of this, maybe using a graph neural network? So there's a bunch of tools to throw at this. I think it would be nice if we can figure out a way of kind of finding the underlying principles that are more than just putting together a lot of stuff. I'll skip a few other things, and thank you very much for taking the time to listen to me.
Before we go for lunch, is there any question for either Roy or Thomas?
The case of quantitative biology, the study of ecosystem, is one problem which is really inferior. So people think that the Lochner-Volterra equation are the good equation for the dynamics of species. So they have the data of the abundances, and they want to infer the property of the coupling constant, the Lochner-Volterra equation. And I think this is a real problem on people, which people would like to have, very efficient methods. So maybe, there are experimental data, and so maybe you could try to use your method.
Yeah, it's a very interesting
I don't know how many particles, in your example, how many particles can you treat?
So we looked up to 35 in this example, but there's no particular limit to that. It was just based on the data we had. But it does definitely get more challenging because you have to basically infer pairwise interactions for n square potential candidates, unless you can have some kind of template of, say, if you have a prior sparse template of things you can already exclude that don't interact because they're far apart, according to some kind of measure, then you can simplify the problem a lot.
So maybe you could already try with random Lotka-Volterra equation with random interaction and see if you can get them with, I don't know, 200 species. And if your answer is yes, then you can really take the experiments and use the...
Very exciting, yeah. Thanks.
So we start with something that is completely free, and then we're trying to. It's completely free, but there's some smoothness that you impose, and then there's versions where you can impose more on it. So you might think that about something that looks like a Wasserstein distance or something like that, because there's something moving around. So that might make more difference. So we're kind of going a little bit in that direction. So I would see the learning in a few places. One is you get some blurry version of something, and can you get a less blurry version of it, or can you say there's something going on in this area, and I think it's a deformation of this type, or something like that. Or you could say maybe we can use kind of a graph model for the actual atomic structure. So I can see basically like kind of any technology fitting in different places in this problem. It would be nice to have kind of a more fundamental view of